This morning, our first speaker, we're very welcome to have Christian Gaetz, who will be telling us all about Bruhat interval polytopes, one-skeleton lattices, and smooth torus orbit closures.
All right, thank you. Can everybody hear me? Great. All right, so I will start off by telling you what Bruhat interval polytopes are, and to do that, I first have to tell you what Bruhat order is. So we've already seen this a little bit today. This is the partial order on the symmetric group, which tells us about containment of Schubert varieties, but it can also just be described completely combinatorially. So this is a partial order on the symmetric group. I have cover relations. A permutation is less than a permutation multiplied by this transposition. This is a cover relation whenever the length increases by exactly 1 when I do that. And here the length is the number of inversions of W, or equivalently the fewest number of these simple transpositions that I need to write W as a product. So here's a couple pictures. On the left, this is Bruhat order for S3. So notice these posets are graded by length, so length 0, length 1, length 2, length 3, and so on. So this is S3 over here. And on the right, this is S4, and you can see already it's getting quite messy. All right, so what is a Bruhat interval polytope? These first appeared in work of Kodama and Williams, and I'll say a small word about why they were studying these later, but for a permutation, V, the Bruhat interval polytope is the polytope inside Rn, whose vertices are all the permutations less than V in Bruhat order. So I take a permutation, I write it in one-line notation, view that as a vector. So the permutation 3, 1, 2 is the vector 3, 1, 2. I look over this whole set of permutations, and I take that convex hull. So all of these permutations will indeed be vertices of this polytope. Probably, or definitely the best known example of this is if V is W naught. W naught, this is the top permutation. This is the reverse permutation, n minus 1, all the way down to 1. In that case, every permutation is less than W naught. So this is the whole symmetric group, and I'm taking the convex hull of all permutations. That's a very well-studied polytope called the permutahedron. So that's what, this is a picture of the permutahedron, where I've kept, as for the posets, I'm drawing the vertices of this sort of on levels corresponding to their length. So this is a polytope with the dashed edges in back, but we can also view this as giving us a partial order on the symmetric group. Right? If I take the edges of this polytope to be the cover relations of a partial order, I have a partial order, and it's different than the Bruhat order that I showed you a few slides ago, which, if you recall, had a lot more edges than this. So this is a weaker order, and in fact, it's called the weak order, or weak Bruhat order. And so we're going to be generalizing that in this talk. So first, just a brief discussion of why people started studying Bruhat interval polytopes. So they are moment map images of various spaces. So one is the totally non-negative part of a Schubert variety. These are the same Schubert varieties that have shown up a few times already. Another is as the moment map image of a torus orbit closure in that Schubert variety. So essentially what that means is there's an action of diagonal matrices, the torus, on these varieties, Schubert varieties. If you take a generic point in the variety and look at its orbit under this torus and take its closure, and if you want to understand the torus orbits inside that closure, understanding how those are arranged is exactly the same as understanding how the vertices and edges and higher dimensional faces of these polytopes are arranged, because an I-dimensional face corresponds to an I-dimensional torus orbit. They are Coxeter matroid polytopes, for those who know what that means. And they're also, in a special case, isomorphic to something called a bridge polytope, which was also studied by Lauren Williams and is connected to plate graphs, which I'll touch on briefly later. All right, so what can we say as far as basic properties of these polytopes? So the first important thing is that they are what are called generalized permutahedra. So I told you they are generalizations of the permutahedron, but there's actually a technical definition of what it means to be a generalized permutohedron, and these are that. So in particular, any edge of one of these polytopes is a Bruhat cover relation. So it is one of the edges in that first very busy picture I showed you on one of the earlier slides. But as we saw for the permutohedron a couple slides ago, not every Bruhat edge, in fact, appears in the polytope. Another equivalent way to say what it means to be a generalized permutohedron is that if we think of the normal fan of this polytope, it coarsens the braid arrangement. So the braid arrangement is the hyperplane arrangement with these hyperplanes where two coordinates are equal to each other. That arrangement divides space into n factorial regions, one for each permutation, which tells you the relative order of the coordinates in that region of space. So since this normal fan coarsens that braid fan, what I mean by that is the top dimensional cones of the normal fan of this polytope are unions of the cones that I just described corresponding to permutations. So this polytope gives us an equivalence relation, which I'll call theta, on the symmetric group, according to which of those cones get glued together in the normal fan. All right, now I'll move on to talking about one skeleton posets. So as I mentioned before, when we have one of these polytopes, we can view it as defining for us a poset by taking the cover relations of the poset to be the edges, in the polytope. So as we saw a few slides ago, in the case V is W0, we recover the weak order. But in general, this is going to be a partial order which is intermediate in strength between the weak order and the strong order. So all of its edges, if you recall from the previous slide, are Bruhat covers, but not every Bruhat cover leads to an edge. However, every weak order cover does lead to an edge. All right, so here's a non-trivial example. So here is the case V equals 3, 4, 1, 2. So we can view this as a three-dimensional polytope by having the dashed things in the back, but we can also view this as a poset where all of these edges, including the dashed ones, are cover relations. All right, so one thing I want to or a couple things I want to draw your attention to. One is that unlike the permutohedron, this is no longer a simple polytope. So this is a three-dimensional polytope, but this vertex here and this vertex here have degree 4. They're incident to 4 edges. So it's not a simple polytope. Another thing I want to draw your attention to in this example is that this poset, like the weak order, is a lattice. So any two elements in this poset have a unique least upper bound and unique greatest lower bound. And those are both questions that we're going to explore further. All right, so first, in order to have some tools to think about this poset that we've just defined, we have this proposition. So remember that the poset for W0, that's just weak order. And we had this equivalence relation theta coming from the normal fan. So this is some equivalence relation on permutations. This proposition says that this poset is the quotient of weak order by this equivalence relation. So I'll show an example of that soon, but this should worry you slightly because in general, you're not just allowed to take quotients of posets by equivalence relations and end up with even a poset, let alone an interesting one. So there's something that goes into saying that this is even a well-defined thing to do. Each equivalence class, so I'll write this for the equivalence class of a permutation X under this equivalence relation, contains a unique element from the interval that's defining the polytope. And for those who think about these kinds of things, that map is what's usually called the matroid map for a matroid polytope. Okay, so let's look at a picture here. So on the left, this is weak order. So this is the whole thing. The colors denote the equivalence class as theta. And on the right, this is the example we saw before of the poset for 3, 4, 1, 2. So this thing is a quotient of this thing. in the sense that, say, this blue guy is less than the orange one because some element of the blue equivalence class is less than some element of the orange equivalence class in weak order. So for example, 4231 is less than 4321, which says that we need to include this order relation here. However, it's not actually true that 2413 and 3412 are comparable in weak order themselves. So that this edge here is an extra one that was not contained in weak order, but which appears in this Bruhat interval polytope. Okay, so in order to extract some consequences of this, we're going to need to study this equivalence relation a little bit more closely. So one non-obvious fact about the equivalence relation is that each equivalence class contains a unique minimal and unique maximal element, which I write bottom of x and top of x. So the existence of the bottom element is relatively easy, but the existence of the top element is actually much harder to show and is a key tool in understanding these polytopes. So just to pull up the same picture again, we see each of these equivalence classes has unique minimal and unique maximal element. Okay, so as I alluded to before, the weak order is known to be a lattice. This is a very well-studied lattice. People have studied lattice quotients of it. So a consequence of some facts about this top map are that the same is true of this one skeleton poset on any Bruhat interval polytope. So the key fact is that this map top, which takes an element to the maximal element in its equivalence class, is order preserving with respect to weak order. So if A is less than B in weak order, then top of A is less than top of B. That's not true, for example, of the bottom map. So this is an interesting property that this top map possesses, and this allows us to, in fact, explicitly describe what is the join relation in this thing that we now know as a lattice, PV. What you do is you take x and y, the things you want to take the join of, you take the top of both equivalence classes, you take their join in weak order, and then you take the bottom of that equivalence class. So because this join exists, this poset is a lattice. But I should warn that the meet operation, so the greatest lower bound operation, does not come in this way from the operation on weak order. So this is a quotient poset of weak order, which is a lattice, but it is not a lattice quotient of weak order. I guess we could call it a joined semi-lattice quotient of weak order. So I think an interesting question would be, people have studied a lot about classifying lattice congruences on weak order, but there might be a broader class that's worth studying that includes these. Okay, so just a couple examples of this lattice operation. So if we take a join of a bunch of atoms of this poset, so elements of rank 1 of this poset are simple reflections, so reflection swapping I and I plus 1. It's a theorem of Billy, Fan, and Lasson. I don't know how to pronounce that name, I'm sorry. They prove that for any subset of the atoms, there is a unique longest element generated in the subgroup generated by those atoms, which lies below V. They call that element MVJ. And in this poset, that element is just the join of the atoms in question. Another example is that when V is a Gauss-Money permutation, this polytope is isomorphic to something called a bridge polytope, which Fraser had previously conjectured would be a lattice, and so which is a special case of the previous theorem. So just a little bit about these bridge polytopes. So there are something called BCFW bridge decompositions, which have appeared in the recent work relating scattering amplitudes in physics to graphs like this called Plavet graphs. So these give you a way to build up a Plavet graph out of smaller pieces. And what Lauren Williams noticed was that for something called the bridge polytope, which is isomorphic to a Bruhat interval polytope with a unique descent, maximal chains in this poset correspond to these bridge decompositions of playback graphs. So for example, this chain here, if you keep track of which labels are switching, tells you how to draw these bridges. So this poset is in a lot of ways analogous to the weak order in that chains in the weak order tell you how to build up permutations. They're reduced words. Chains in this poset tell you how to build up playback graphs in a similar sort of reduced way. It sort of extends the analogy to see that, in fact, they both have this lattice structure coming from being special cases of Bruhat interval polytopes. All right, the next direction I want to go in studying these polytopes is to look at the degrees of these vertices. So remember, we noticed earlier that these polytopes are not necessarily simple. So this is a polytope in three-dimensional space. If it were simple, all vertices would be incident to three edges. But in fact, that's not true because this guy and this guy have degree 4. The theorem is that this degree function, the function which for vertex asks how many edges are you incident to, is actually monotone with respect to this partial order. So if we look at a vertex which is less than another vertex in this partial order, then its degree will be at most the degree of the other vertex. So in particular, the vertices that we notice that have degree 4 form a order filter in this poset. And as a consequence of that, we can resolve this conjecture of Lee and Masuda. So just a bit about the geometry. So recall there was the Schubert variety, and we wrote Y for this orbit closure inside it. This is a toric variety, which is associated with the Bruhat interval polytope. So faces of the Bruhat interval polytope correspond to torus orbits. And a simple polytope corresponds to the toric variety being smooth. So they had conjectured that the polytope is simple if and only if it's simple at the top vertex. That is, if and only if the top vertex has degree equal to the dimension of the polytope. Or equivalently, that this variety is smooth if and only if it's smooth at a particular torus fixed point. So this monotonicity theorem, this implies their conjecture because if the top vertex has degree equal to the dimension, well, it's always the case that the bottom vertex has degree equal to the dimension, so by this monotonicity, everybody has degree equal to the dimension, and it's a simple polytope. So that answers that question. Okay, I have only about a minute left, so I'm not going to have a chance to go too much through this last section, but there's a sense in which these polytopes are, although they're not simple, they're always what I call directionally simple. So any subset of the edges going in the upward direction from a vertex span a face in the polytope. What that means is that if you define the h vector from the f vector via the usual formula, this is normally something one only does for simple or dually for simplicial polytopes, you still get coherent numbers out. So the h vector is still positive, even though it's not a simple polytope, and in fact, the h vector has a nice combinatorial description in terms of counting descents after having applied this top map. And I think I'm out of time, so thank you for your attention.
Are there any questions?
Does it ever happen that your polytope is simple, which is to say that the edges coming out of the vertex are Q bases, but aren't the Z bases?
The question was, is the polytope ever simple so that the edges coming out of a vertex are a Q basis, but perhaps not a Z basis? And I think the fact that it's a generalized permutohedron, so these edges are they're parallel to roots, but they're not roots on the nose. So I guess what you said is possible. I haven't looked at that.
Along what you're looking at, you can ask about reversible polytopes from U to B instead of like starting from the identity. Can you say anything about those?
Yeah, so the question is, One can also look at Bruhat interval polytopes, which are the convex hull of an interval in Bruhat order, which is not necessarily from the bottom up to some w, but from some other interval. The theorems are not true for those. So they are not, the one skeleta are not lattices. There is no degree monotonicity. And that's why they're not included. Sam?
Do you know anything about the Mobius function of these lattices?
Sam asks if I know anything about the Mobius function. So the fact that it is the semilattice quotient, if I recall, I think that tells you that the Mobius functions starting from the bottom up to some element are predictable as they are for weak order. But I think because the meets are not nice, that's not true of arbitrary Mobius functions. And so, yeah, it would be interesting to investigate what one can say about the arbitrary Mobius functions.
Are these polytopes particular instances of Markovitch alone in polytopes?
The question is whether these are instances of MV polytopes, and I don't know the answer to that question. Alan is shaking his head.
Yeah, so I think you had said that this, the polytope, like the coset from it is the image of the bottom map, is that right?
That's right.
Yeah, so then do you know anything about like what the image of the top map is then? Is that something else that you...
The question is if I know anything about what is the image of the top map. No, I don't know much about that.
Like in one of the things in that last section, you had something where something was determined by the number of descents of up top of something. So I wonder if that's related to what sort of what permutations are.
Right, yeah, that's an excellent question, is to understand more concretely what is the image of this top map, but I don't know the answer to that question. Yes?
So you said the degrees of the vertices get higher when you go up. So is it true that the set of vertices that you find as corresponding to the orbital perimeter also get larger?
Sorry, I'm not sure I caught that.
So can I go to the last slide? Yeah. So for example, the blue vertex corresponds to some vertices that general to the orbital perimeter.
Mm-hmm.
Does this set get bigger as it goes up?
Okay, the question is whether the equivalence classes defining these vertices get bigger as you go up, and the answer to that is also yes. Yeah.
Is the orientation you get that gives a lattice coming from some linear function?
The question is whether this orientation that I've drawn all my polytopes in comes from a linear function. The answer is yes, that orientation does, but I've been cheating by drawing everything of the same length at the same level. That's not actually geometrically possible, but there is a linear function which gives the correct orientation to all the edges, yes. Oh, yes.
I'm not sure if you said this, but if your polytope is simple, then it is true the Mobius function has to be 0 plus 1 or minus 1. We can talk about that.
Okay, yeah, there's a comment that if the polytope is simple, then the Mobius function has to be 0 plus minus 1. You know, given the stickers we all just got, I'm a little disappointed. Nobody has asked me, what about other types? The answer is, I think the theorems are true, but I haven't looked too much into it.
The stickers work, we don't need to ask.
Exactly. Yes. Yeah, that's right. I mean, you could look at other finite Harksler groups. You could take the half sum of the positive roots and look at orbits of them under the elements in a Bruhat interval and take those as vertices, study that polytope. Yeah. The question is, what about the polytopes for arbitrary dominant weight? So here we can think of the permutations as having acted on the weight 1, 2, 3, so on up to n, and gives us the point and weight space that we're taking the convex hulls of. You could take some other weight there. For example, some of the entries could be equal. So for example, then you would get Bruhat interval polytopes, which correspond to usual matroids in the Grassmannian, for example. Those things actually are less nice. Yeah, so at least some of the results fail for that. I forget exactly which ones remain true. That's a great question.
All right, I think we are out of time, so perhaps we can save any additional questions till afterwards, but let's thank Christian again.